Imagine I would like you to name something small, very small. You'll know that I'm not talking about your fingernails or your hair follicles. So, you say something subatomic. It's literally part of an atom. So, what about this guy right here? An electron. Check these out. This is a table of some common subatomic particles in the universe. And look at this group. They're called neutrinos. What neutrinos are, they basically are ghosts. They don't interact with anything, they're completely neutral. So, not much of interest here, right? Well, here's something interesting. These neutrinos have been found to oscillate, or in a layman's terms, shapeshift. And according to the laws of physics, to do that, you have to have mass. First, let us familiarize ourselves with the concept of beta decay. Beta decay is when a neutron or a proton turns into each other. In the case that we're about to explore, we're dealing with beta minus decay where an electron is ejected and a neutron turns into a proton. A good analogy for this situation is seeing something shoot out of a cannon. That's how you can interpret the electron. And soon we'll see the neutrino as well. Meet tritium, a cousin of hydrogen, also has one proton. But the difference is tritium has two neutrons. This is incredibly unstable. Hence, one of the neutrons undergoes beta minus decay and turns into the proton. But that's not all. In the process, an electron and a neutrino were both released during the beta decay. Now, this is the premise of our experiment that we're about to get into. What is the mass of this neutrino? Remember the cannon from earlier? The explosion shoots out an electron, which is called a beta particle, and a neutrino. However, to do this, you need money. No, actually, no, not money. You need energy. However, there's only a set amount of this energy, and this could be the secret for us to solve for the mass of the neutrino. Just one problem. There's not really a whole lot of energy to go around when it's just a singular neutrino. So, come take a look at this thing. It's called KATRIN, spelled KATRIN. It's located over in Germany, and scientists are planning to use this to continue to narrow down the neutrino's mass. Their hypothesis is that they can use this machine to figure out the energy that the beta decay uses. And from that, they can use E equals mc squared to figure out the mass of the neutrino. So, how does KATRIN work? Well, it works like a giant magnet. So it catches the fastest electrons ejected out of the beta decay process and measures their energy. And we know the total energy from the explosion. We can find out what energy is missing because the total energy is shared by the neutrino and the electron. What's missing must be the energy that belongs to the neutrino that we can use to calculate its mass. So, I bet you're now scratching your tongue and you want to know, well, how much is the mass of the neutrino? Well, the big blimpy boy has found that the neutrino has a value of less than 0.45 electron volts. And if you don't know what an electron volt is, that's okay. I don't really get it either. But what it does mean is that it is just about 1 millionth of the mass of a single electron. And that's the method that they used for finding out the mass of the neutrino. And you know what? They're still running that machine today to narrow the figure of 0.45 electrovolts down even more. To propose something that we could do further to understand this topic, we know that the KATRIN's data is open source. So it's possible for us to use artificial intelligence to analyze the data obtained by the machine. This, in combination with human intelligence, could give us some insights on how to improve the experiment and how to drive down the range of values for neutrinos mass further. Thank you guys so much for listening to me talk for, what's it been, 6 minutes? And I hope y'all have a great rest of your day. Thank you.